Hello friends, myself Dr. Vishnu Charan Das welcome you to Chemistry Buzz and my video series on phase rule. Today we are going to discuss and derive Clapeyron Clausius equation, which is very important for study of two-phase one-component system like a solid liquid, that is the equilibrium at its melting point, liquid vapor, this equilibrium at its boiling point, solid and vapor at sublimation temperature, and also the transition of one crystalline form to other crystalline form, that is rhombic sulfur to monoclinic sulfur at transition temperature. So at these points it is very important. The Clapeyron equation is very important. So we should derive the Clapeyron equation, which will be used in the next videos when we will learn one component system, that is water system and sulfur system, carbon dioxide system, etc. So let us derive the Clapeyron equation. So for derivation of Clapeyron equation, let us consider a system of pure substance of one component. So this is phase A, this is A phase, and this is the B phase. The two phases are in equilibrium. Also we can take it as liquid phase and vapor phase. So when the liquid is taken and the vaporization starts, so after some time the equilibrium is attained and the liquid vapor equilibrium is attained. So at equilibrium point we have the delta G is equal to 0. This implies the Ga is equal to Gb. The free energy of phase A is equal to the free energy of phase B. So at this equilibrium point we can transfer any calculated quantity of substance from one phase to other phase thermodynamically reversibly, that is by changing infinitesimally keeping the equilibrium constant. Okay? So maintaining the equilibrium, we can transfer any amount of substance from one phase to other phase. Say this is the pure substance, liquid and vapor in equilibrium, and we want to transfer the liquid to the vapor phase, phase A to phase B. So what we have to do? We have to supply heat to the phase A infinitesimally and reversibly, maintaining the equilibrium, so that some amount of A or some amount of liquid will transfer to the vapor phase. Similarly, we can transfer the vapor to liquid by withdrawing heat reversibly and infinitesimally. So in this way we can change any amount of substance from one phase to other phase thermodynamically and reversibly. So when these two phases are in equilibrium, the free energy of the two phases are also same. So this indicates a pure phase in a pure component in two phases, and when the same amount, then the free energy are equal. So same amount of a pure substance in two phases, then their free energy become equal. So and this equilibrium, say, is maintained at the temperature T and pressure T, and now we want to change the system infinitely, that means the temperature changes by dT and pressure changes by dP. Okay, so the new pressure and new temperature will be T plus dT and P plus dP. Okay, and at this temperature, new temperature and pressure, again the equilibrium will be attained. So when the temperature and pressure changes by dP, the energy of phase A changes by dGA and B changed by dGB. So when at this temperature the equilibrium is maintained, we can write the free energy, that is GA plus dGA is equal to dGB plus GB. Okay. So, and previously we have seen the GA is equal to GB. So GB cancels out and dGA is equal to dGB. So the change in free energy is also same in both the phases. Okay. So here the relationship between the dT and dP, the very small change in temperature and pressure is called the Clapeyron equation, and we are going to derive it. Okay, so from this, for a pure substance in two phases, for a pure substance, the change in free energy we can write the dG is equal to SdT minus dT. Okay, and this is the pure substance in equilibrium in two phases. So we can write the dGA is equal to SA dt minus VA dt, and dGB is equal to SB dt minus VB dt. Okay, so from this equation again we can write SA dt minus VA dt is equal to SB dt minus VB dt. Okay, so rearranging this equation, we can write the VB minus VA dP is equal to SB minus SA dt. Okay, also we can write this the dP by dt is equal to SB minus SA by VB minus VA is equal to the delta S by VB minus VA. So this is your Clapeyron equation. Okay, so this is your Clapeyron equation, and here the VB and VA, this is the liquid phase and vapor phase. So VB and VA are the molar volume. So VA is the molar volume of liquid, VB is the molar volume of gas. Okay. So delta S, that is SB minus SC, that is also difference between the molar entropy of the two phases. So when these two phases are in equilibrium as at its melting point or boiling point, okay, liquid vapor, so this is boiling point. So at boiling point, the delta S is equal to Q reversible by P. Okay, so we can rewrite the Clapeyron equation. We can rewrite the Clapeyron equation, that is dP by Q reversible by P dV minus dV. Okay. So we have taken different system to apply the Clapeyron equation. So for solid liquids, the heat involved, that is the heat of fusion, delta is fusion, and the liquid vapor, that is delta is vaporization, solid and vapor equilibrium, so delta is sublimation, and rhombic sulfur to monoclinic, one crystalline form to other crystalline form, so this is delta is transition. So Q reversible will be of this form depending upon the system. Okay. So now let us consider the liquid vapor equilibrium at its boiling point. Okay. So when liquid vapor, your VA is equal to the VL and VB is equal to Vg. Okay. And in this case, we have already taken Q reversible is equal to delta H V, and Vg is much larger in comparison to VL. So in place of Vg minus VL, we can write this tends to Vg. So for this system, we can write the Clapeyron equation, that is dP by dt is equal to delta H V divided by T Vg. Okay. So this is the Clapeyron equation for your liquid vapor equilibrium. Okay. Now we find that from kinetic theory of a gas, the Pv is equal to Rp for 1 mole of a gas, and V is equal to Rp by T. Okay. So this equation will substitute in the Clapeyron equation here. So in this equation we will replace it the value of Vg. So we can write the equation like dP by dt is equal to delta X by T into P by Rp. So this is equal to delta X by Rp square. Okay. So separating the variables, now we will get dP by P is equal to delta H by R dt by P square. Okay. So we can write this again in this form, d ln P is equal to delta H by R dt by T square. Okay. So integrating both sides, we will get of this equation, we will get dP d ln P is equal to delta H by R integrated over dt by T square. Okay. So this gives ln P equal to delta H by R minus P plus, okay, quantity is the integration constant, and this equation again simplified to give you the ln P is equal to minus delta H by R T plus C. So this is the equation of a straight line, and if we plot the graph, this will be a straight line with negative slope, and the slope is equal to minus delta H by R. Okay. So this delta H is V, heat of vaporization. Okay. And from this we can calculate the heat of vaporization. Okay. Again we will integrate this equation with the limit of imposing the limit, that is when P1 changes to P2 and T1 changes to T2, we get a exact differential. So that will give you the d ln P integrated over P1 to P2 is equal to delta H by R integrated dt by T square T1 T2. This implies ln P1 ln P2 by P1 equal to delta H by R 1 by T1 minus 1 by T2. Okay. So this is your Clapeyron Clausius equation. Clapeyron Clausius equation. Okay, one term, and if we change it to the logarithmic form, then this will be 2.303 log P2 by P1 equal to delta H V by R 1 by P1 minus 1 by P2. Okay. Also we can write this delta H V by R into delta T by T1 T2. Okay. So this is another form of Clapeyron Clausius equation. So from Clapeyron Clausius equation we can compute the value of heat of vaporization and also the vapor pressure of the substance in given temperature if it is given at another temperature. Okay. If you are given T1 and T2 is asking and T2 is given, then it can also be calculated from the Clapeyron Clausius equation. Also, this is applied to study the effect of pressure on boiling point. The effect of pressure on boiling point. Okay. And effect of temperature on vapor pressure, effect of temperature on vapor pressure. Okay. And also the calculation of heat of vaporization. Okay. So these are the applications of Clapeyron equation. Now let us see the application of your Clapeyron equation. Okay. Application of the Clapeyron equation. So the Clapeyron equation is dP by dt is equal to the delta S by dB minus dE. And let us consider the solid liquid equilibrium. Solid liquid equilibrium. Okay. For solid liquid equilibrium, when solid changes to liquid at its melting point, the Vb is equal to Vs and Va is equal to Vl. And here the volume of liquid is more than volume of solid, so Vl is greater than Vs. So this value is equal to positive, and change in entropy when solid changes to liquid, the entropy also increases, so change in entropy is positive. Okay, and dP by dt is positive. Okay, but if we take the equilibrium between ice and water, so water shows the anomalous behavior. As you know, when you move from 4 degree to 0 degree centigrade, the volume of water increases, and it is maximum when it is in ice form. So here Vs is greater than Va. Okay, so for this system we can write the dP, this is Vp minus Va is equal to negative, because Vb is the volume of solid and Va is the volume of liquid, and here the volume of solid is 4. Okay, so this is negative, and for the ice water system we will have dP by dt is equal to negative. So this implies if we increase the pressure, then the temperature will decrease, that is the melting point will decrease, and if we increase the melting point, then the pressure will decrease. Okay, and this finds its application in the adventurous sports that is ice skating. Ice skating, adventurous sports. Okay. So in ice skating, the pressure of the skater exerted on the ice over the skating blade, so that decreases the melting point of ice, and the ice melts to form little water, and that water acts as a lubricant to support the movement over ice, and that is ice skating become possible. Okay, so these are the applications of Clapeyron equations and Clapeyron Clausius equations we have learned in a very easy and interesting manner. I hope you have enjoyed this video, and if it is so, then don't forget to give your like and share among your friends. Thank you for watching.